welcome to Marker Board Videos. Today's video is about thermal equilibrium. And what thermal equilibrium is that's a big physics way of saying that things are even, temperature-wise. There's no heat flow between objects when they're in thermal equilibrium, and that's because they're the same temperature. So there's the same amount of disorder in both objects, and so there's no heat flow. It's thermal equilibrium. It's the same temperature. Big way of saying that. Thermometers work because of thermal equilibrium. What actually happens is a thermometer is a liquid inside of a glass tube, and there's numbers on the outside of that glass tube. That liquid is going to expand or contract based on its temperature. Well, it actually, when you put it, let's say you put a thermometer in a hotter liquid, the heat flows from the hotter liquid to the colder liquid, causing that colder liquid to expand, and the temperature rises. And when they're in thermal equilibrium, that heat flow doesn't occur anymore, and you can look at the thermometer and see how much it's expanded, and that tells you the temperature. Likewise, when you're putting a thermometer in a cooler object, the heat flows literally from the liquid inside that glass tube into the liquid around it, and it causes that liquid in the tube in the thermometer to contract, to get smaller, until they're in thermal equilibrium. When they're in thermal equilibrium, they're the exact same temperature, exact same, and then you can actually read the thermometer and read those little marks we put on the outside of that glass, and that tells you what the temperature is. So a thermometer works because of thermal equilibrium. The big way of saying all of the heat in a substance, all of the energy in a substance, is to call it internal energy. So internal energy, if you could take every single molecule, figure out how much energy it has, add it all up, that would be called the internal energy of an object. So if it takes in heat, it actually gets warmer, right? The internal energy is going to go up. Well, that makes sense because the motion of the particles increase, the kinetic energy increases, so the internal energy is going to increase. If it gives off heat, internal energy is going to go down, and that also makes sense because things slow down then. The unit for heat is a joule, Joule, because it's energy, and the unit for energy is joule. The abbreviation is uppercase J. We can actually calculate how much heat has been transferred from one object to another if we look at a couple of different things. We have to look at the temperature change. Where did it start out and where did it end up? We have to look at what it is, because that's going to make a big difference. And we have to look at how much of it we had. So if we have a bathtub of water versus a swimming pool of water, and they both have the same temperature change, well, the temperature change is the same, the substance is the same, but the mass is significantly different. So you're going to have a big difference in amount of heat transferred. Likewise, if we transfer heat, let's say we have 5 grams of water and 5 grams of iron, and they both change the same temperature, now the difference is the substance, and that's going to make a difference too. The amount of heat needed to raise 1 gram of water 1 degree Celsius, specifically from 3 degrees Celsius to 4 degrees Celsius, is how we define 1 calorie. Now, I know that you're familiar with the term calorie because it's in our food, it's in when we work out, you're on the treadmill, it says you burn so many calories, so I know you're familiar with that. But the scientific term is it's how much heat is needed to raise 1 gram of water 1 degree Celsius, 1 calorie. Well, 1,000 calories would be 1 kilocalorie, right? If you look at the back of your food, or you look at the nutritional information when you go to a restaurant, you'll see that food calories are given in the word calorie with a capital C. If it has a capital C, we're not really talking about calories anymore. We're talking about kilocalories. So if you eat something and it says it has 692 calories with an uppercase C, that's actually 692,000 calories. So I want you to know that, yes, it doesn't take a lot of heat to raise 1 gram of water 1 degree Celsius, and so you may think 1 calorie is not very much, and it is a relatively small number. But when you look at your food, go ahead and take a look at any food that you have in your house. You'll see that the calories and the nutritional information are given with an uppercase C, not a lowercase c, and that means kilocalories. So while we're talking about heat and heat transfer, if you've ever eaten a piece of pizza, and I know we all have, and you eat it when it first comes out of the oven, you put it in your mouth, you burn the roof of your mouth almost every time. So why is that? Well, sometimes students tell me it's because the cheese is a different temperature than the crust, but that's not true. You could actually test it and see that the temperature of the cheese and the temperature of the crust was exactly the same. Some people say that your tongue is better at handling heat than the roof of your mouth, and scientists have also proven that that's not true. So what's different? What's different is cheese versus crust. And cheese wants to give up its heat a lot easier than crust wants to give up its heat. And so that cheese gets in contact with the roof of your mouth. The roof of your mouth has less energy. It's colder, so the heat goes from the cheese into the roof of your mouth, whereas the crust holds onto its heat a little bit better. That's called the specific heat capacity, or thermal equilibrium, also known as thermal laziness. So things, remember inertia, things want to keep doing what they've been doing. Well, in terms of heat, do you want to stay the temperature that you are, or do you want to get rid of your extra heat if you're put in contact with something cooler? Some things do that really easily. Some things it's much harder to do. For water, for example, has a specific heat capacity, 1 calorie per gram per degree Celsius. But steel has a specific heat capacity of 0.1 calories per gram per degree Celsius. Much easier to heat up one of those than to heat up the other. And I'm going to leave it up to you to figure out which one takes less energy to heat up. I think by looking at this number, it's pretty obvious. And one of them is about 10 times easier than the other. That's what happens with the cheese and the crust. The cheese is more likely to give up its heat and gives it up much easier than the crust will.